Amanda or Chad. Bridget just walked in. Anne. Reagan is okay. No, he is here. Gotta say something, dude. When I say you're not here, Diksha. Is Diksha here? No. And Jaron.
Yeah.
Twisson. Yeah. Here. James. Okay, and there's Edward. Okay, so getting started. Yes, I really am going to use this picture today. We're going to talk about angular momentum and the conservation of angular momentum. And so to start off, here's the picture that we ended with last lecture with the figure skater illustrating conservation of angular momentum. Now we're going to do a demonstration with this to make sure we understand it. But first, just the equations. Newton's second law. What is Newton's second law? Normal second law. Sum of the forces equals mass times acceleration. And then we learned a second version of it, which is actually the more precise version, but chronologically it came second because we didn't know momentum yet. Change in momentum divided by change in time. For rotation, we have an equivalent to Newton's second law, which you've already studied in your Flip Friday. And that was replace the force with the rotation equivalent of force, which is torque. Replace the momentum with the rotational equivalent momentum, angular momentum, L. And you have this equation here. So that's the rotational equivalent to Newton's second law. And just like with collisions, when we talked about collisions, we talked about momentum being conserved. And we took this top equation, we said, well, change in momentum is the net force multiplied by the change in time. So if the net force is 0, then momentum will always be conserved. So if I take a system that includes two objects hitting each other, and the objects have minimal friction with the ground, then I could say momentum is conserved for that collision, especially with delta t being small. So with rotation, we do exactly the same thing. We take this equation and solve it for change in angular momentum, and what condition is necessary for the change in angular momentum to equal 0. The net torque would have to be 0. That's just a straight analogy. So if the net torque is 0, then angular momentum will be conserved. Now, one last thing before we go to doing a demonstration here. Notice that angular momentum is a vector. So angular momentum can be conserved in the x direction or the y direction or the z direction. So for our experiments, or our demonstrations, I'm going to need somebody to come up here and basically sit and spin. Who wants to come sit and spin? Thank you, James. So, he's going to spin. Now, when he sits on the chair and when he doesn't have his feet on anything, you might want to adjust the height so you don't have to, do too much to keep your feet off the ground. So when he's sitting here and when he takes his feet off of that, he will be free to rotate about the vertical axis. So that means there's no torques about the vertical axis. If there are no torques about the vertical axis, that means that his angular velocity about the vertical axis, angular momentum about the vertical axis should remain constant. So we're going to play around with this, and we are going to have our official class videographer here take video of, I think that's the camera I want. No, I want which camera I want. Well, we'll see. Okay. Just keep it on this gentleman. Now, because I have a big
How do I switch to recording? How do I switch to recording? Wait, how do I switch it to recording? Because if I pressed the camera button and it just took a picture instead.
Oh.
And there wasn't an obvious little red dot thing to
okay.
put on instead,
So, well, I'll try a different camera. How's that?
Sure. The blue one with options.
There's a different camera.
Let's see.
Okay, so he's holding these, hold one in each hand.
Wait.
One in each hand, and now I'm going to rotate him.
Which one was it? Nope, still camera.
Yeah, don't press any buttons.
Oh, so if I... You think it'll actually record?
Press the X button.
I am.
I think it will continue.
I am pressing the X button. I'll press the
Press
X
the
button.
X button.
Yes. It doesn't like my thumbs, I think.
Okay.
Okay.
Okay. So, back to James, who's now getting dizzy. Okay, he's spinning. Now, put your arms out. What happened when he put his arms out? Okay, now bring him back in. He sped up. Okay, now go ahead and give me that back. I'm going to have you stay up here, James. You can set those down, though. You don't have to keep a... So, what we saw was when he put his arms out, he slowed down. When he brought them in, he sped up. Why? It's actually, he did do work when he brought them in, but that's not the key I want to focus on, because that doesn't actually tell you if he's going to go faster by itself. It takes a little more calculation than just that. So, now I'm trying to figure out where I put my stylus. Here it is. When he brought his hands in, what did he do to his moment of inertia? He decreased it, because the moment of inertia has the equation I is equal to the sum of mr squared. Now his body has its own moment of inertia, and we're just going to say, well, that's a constant, and then consider what was going on with his hands. When he put his hands out, he increased the radius for that. Those are pretty significant masses he was holding, 5 kilograms or about 11 pounds each. And so when he took those away, that really increased his moment of inertia, but we established his torque about the vertical axis was 0. So that means his angular momentum about the vertical axis, and remember the right hand rule, if he's rotating like this, he has an angular momentum that's pointing up. If he's going like this, he has an angular momentum that was pointing down. So he had an angular momentum pointing down because I had him spinning this way. That stayed constant when he increased his moment of inertia, since angular momentum is equal to moment of inertia multiplied by angular velocity. When the moment of inertia increased, then you have to have a decrease in the angular velocity to keep a constant angular momentum. Now, of course, we can do this the opposite way. Won't worry about taking pictures with this one. So start your arms out. And then I spin him with his arms out. And then I have you pull them in. He speeds up a lot, right? Now, I had an answer about energy, and with kinetic energy and work, when he's spinning, these want to go what direction? They want to go in a straight line, so they want to go like that. And so he has to put an inward force to keep them from going in a straight line. Well, when he pulls them in, that means he's putting a force that's inward, and they're moving inward. He's doing a positive work. So when he brings them in, his kinetic energy is increasing. But his kinetic energy is 1/2 I omega squared. And if you just say, well, kinetic energy increased, either I could have increased or omega could have increased. You have to look at the angular momentum, or the moment of inertia, to solve out, oh, that's what's going on. Okay, when he went out, his force that he was putting on these was still inward because they wanted to go out. So he's putting an inward force, but the direction was out, the motion. That was a negative work that he did. Hence, he loses kinetic energy. Now, I'm going to go straight from that to this. A wheel. I'm going to have him hold the wheel. Go ahead, both sides. Both sides. We don't want to make it too hard on you. Okay, so right now, angular momentum is completely 0. I'll start spinning this. What direction is the angular momentum of this wheel? That's correct. You take your right hand, curl your fingers the direction it's rotating, and the angular momentum is pointing that direction. Now I'm going to have him rotate this. Just put this hand down and that one up. So you're going to keep going. Get it over. There we go. Okay, so now what happened when he did that? You can see this isn't completely frictionless because he's slowing down. He started rotating, right? And I see Lindsay using her hands to indicate the angular momentum that his body had was downward. What direction is the angular momentum of this tire right here? It's upward. The reason he started rotating, go ahead, your feet are not touching, right? Go ahead and bring it back down. I should flip it all the way over. What's going on here is, once again, angular momentum in the vertical direction is roughly being conserved. You can see friction is stopping him, so he's not completely conserved. So as angular momentum is conserved, he started with angular momentum to the left. And then he rotated so angular momentum of the wheel was up, so he had to rotate so his angular momentum was down to counter that. Then, because he was stopped back to zero angular momentum, he changed it from the wheel being down to the wheel being up, and he had to go twice as fast to counter the change in angular momentum. So that's all my tricks for you. Thank you very much. Now, there are cool interactions between torque and angular momentum. If you look at this equation once again, change in angular momentum is equal to net torque multiplied by time. So we can take something like this and say, okay, I'm going to get it spinning, and then I'm going to hold it just by having my fingers in this loop. What direction is the angular momentum of this wheel right now? Okay, it's going that direction. What direction is the torque caused by gravity about this loop? Torque is R cross F. So you put your fingers first in the direction of the radius from the axis out to where the force of gravity is acting, which would be the center of mass. And then orient your hands so your fingers can bend in the direction of the force. Your thumb points to the rear of me. So I have a torque that's pointing to the rear of me, and an angular momentum that's pointing that direction. So when I let go with my hand and just hold the loop, there we go. It starts spinning as it falls down. Notice it fell down much slower than it would have fallen if I didn't have it spinning. Why? It's on the screen behind me. My angular momentum was initially pointing that direction, but the torque was pointing behind me. And from that equation behind me, the change in angular momentum is going to be in the same direction as the net torque. And it's proportional to the torque. So a bigger torque would mean a bigger change in angular momentum per second. So since the angular momentum change is pointing the same direction as the torque behind me, if angular momentum is pointing that way and it's going to change the point behind me, this tire is going to have to rotate because its angular momentum is always going to be parallel to this axis. And so the tire rotated because of the torque. We call that precession. And you probably have noticed that when you spin a top. A top doesn't just spin straight up and down. It starts going around a circle. And it's going around a circle. We call that precession because of the torque of gravity trying to make it tip over. And instead of tipping over, it starts rotating instead. And as it tips a little more, it rotates a little more. Question?
Doesn't the torque change directions though as it?
Yes, the torque is constantly changing direction as it rotates. And so it just constantly is going around a circle. Okay, one more relationship on this. We all can ride a bicycle. Many people can ride a bicycle without hands. When you ride a bicycle, you've got the tire spinning like this. What direction is the moment of inertia, or excuse me, the angular momentum of the tire? It's going that way. Now, if I lean left, now I'm going to have a torque that, just like when I held this side up, is to my rear. So what's that going to make the tire do? What happened in this case, now it's spinning really slowly, so not much is going to happen. But what happened when I just support it, here, I'll speed it up. What happens when I just support it out here and I have the torque caused by gravity? What did it do? It rotated because the change in angular momentum is in the direction of the net torque. So when you're riding a bicycle, your angular momentum is always to your left for the tires. When you lean left, you create a torque to the rear. Now the back tire is fixed and can't rotate, but the front tire can, and so the front tire is going to go like this. And so the front tire turns left because you lean left. And if you lean right, that creates a torque to the front, and so this moves to the front when you lean to the right. That's a big part of the reason you can ride a bicycle without your hands. Most of us, even with our hands, can't balance a bicycle standing up. Having this angular momentum makes everything a lot slower in response. Having the rotating tire, because you have the time for the response, depends on the torque and the angular momentum. The faster you go, the slower the response is going to be. Now, a number of years ago, Heather Holweger, a student, said, so how come when I ride a motorcycle on the freeway, when I want to turn left, I push the left side of the steering wheel forward? Now, I've never ridden a motorcycle on a freeway, and I was like, what, you do? So I had to go look it up, and yes, they do. And it's a little more complicated. When you push the left side of the steering wheel forward, you're going to immediately cause the motorcycle to tip, and the tip causes it to come back. So you push the left side forward, the motorcycle tips to your left, which makes the wheel come back on you. And that's apparently how people steer on motorcycles on freeways. I don't ride a motorcycle on freeways, so don't know. What was that?
Push that left handlebar forward, it'll dip me into an angle.
Yeah.
And if I hold it steady, I keep that angle. You push it farther, you go farther. If you bring it back, you stand back up.
Yeah.
But I feel like I'm not actually bringing the tire back.
Well,
I am, and I don't notice.
You're pushing forward and making the tire rotate just a little. The tire rotating just a little is enough to make the motorcycle lean over, which actually makes it then rotate back the other direction.
Even if I don't realize I'm doing it.
Yeah. Okay. Clicker question. It's not open yet. What condition results in angular momentum being conserved? Waiting on one. There we go. Okay, so we had 3, 1, 1, and 16. The no net torque was the correct answer. Linear momentum is conserved if there's no net force. Angular momentum if there's no net torque. Okay, it is time to do our post test. So I had a problem, homework problem all ready to go, but time be what it is. Okay, so when you get your test, go ahead and start. It's a 30-minute test. This is just the same test you did before for extra credit. You don't need anything except for a pencil or pen. Please only write on The Scantron form run on the test forms. You can use a pen if you want. No. Don't write on the test forms. This is just multiple choice.
So how does the extra credit work? Is it whatever we got this time subtracted from last time?
No.
Or is it whatever we got right?
There's a maximum of a half point of extra credit for each time. For the entire class. Yes, I am. I scanned it with my. Remember, these numbers only are meaningful for this, so that's the reason I'm not keeping them confidential, because the numbers will never show up anywhere. same assumptions that we've been using in class everywhere else about air resistance and that kind of thing.